Hello, dear students. I'll be giving you a lecture series in quantum mechanics, and this course content of these lectures is the part of Btech first year engineering physics course that we offer in our institute. Now, before I start the course, as a student, you'll be curious to ask a question that why should you study quantum mechanics in engineering course? What is the need of studying quantum mechanics? Dear students, let me tell you that the progress in engineering is dictated by progress in physics in particular. It was Newtonian mechanics that revolutionized the way of our living through its applications. The theory of electromagnetism gave birth to communication and power engineering. In the last 100 years, it is quantum mechanics that is shaping the different branches of engineering. For example, the electronic industry has been possible through our understanding of quantum theory. Material science, as you know, is exponentially expanding because every day we are having a better understanding of how atoms and molecules act when they are in clusters. And all the phenomena at the cluster level, at the smaller scale, is dictated by the principles of quantum mechanics. So it should be now very clear to you that why we study quantum theory. Not only that it is so useful in fields of engineering and technology, it's also thrilling to go through the principles on which this theory is based. So now we begin our lecture, as our first lecture would be introducing you with the subject, going through the basics of the subject, and then we will build up as time progresses. So the first question that one may ask now is that, what is the difference between classical mechanics and quantum mechanics? Normally, classical mechanics, we refer to the physics that was there before 1900. After 1900, there were a series of experiments that challenged the physics known at that time. And then our new concepts were shaped. The adventure of going through those concepts is what we now call as quantum mechanics. Quantum mechanics normally would deal with the physics at the microscopic level, because the phenomena at microscopic level are very challenging to understand, and new principles were developed in order to get a better feeling of these phenomena. Before 1900, physics was there were two fundamental concepts in physics. The first concept was the concept of particle. Now, particle was something, it was representing a system. For example, even your Earth is a particle that is going around the sun. Any system can be actually visualized as a single particle. And then that single particle can then obey the laws of mechanics. And the laws of motion dictate us the dynamics of that particle. For example, if you have a body of mass m and you apply force on it, how would its dynamics evolve? It will be given by the three laws of motion. Then there was another concept, that was the concept of electromagnetic waves. This pertained to the physics of the light. So we have light, and that's coming from the matter. This light is massless, and its behavior is different from the material particles, or we call as particles. So how would we understand the behavior of light? And the theory that was shaped to understand the optical phenomena, or the phenomena concerned with light, is called as the electromagnetic wave theory. So in principle, before 1900, there were two powerful pillars of physics. One was the concept of the mechanics, particles, which was dealt with the concepts of Newtonian theory, and the other was the concept of the electromagnetic waves, which was dealt with the Carl Maxwell's electromagnetic theory. The most important idea in physics was that the world is deterministic. That is that if you know the initial conditions of any system, you will be able to predict its future. For example, we are able to tell when the eclipse will happen, exactly and precisely, date and location. The reason is that because the Newtonian mechanics predicts completely future if the initial conditions are properly understood. Then you may ask a very simple question that suppose you toss a coin, then it could be either head up or tail up, so we don't know the future. Even if the coin is classical and the kind of laws it obeys are classical in sense. Now here, the problem is that we don't know the exact initial conditions, because this system is so complicated that when I toss the coin up, the coin strikes with the molecules of the air, then there is the wind speed, then there is the temperature, and then it hits the grass, and in a very complicated way. And there are many things that will control the outcome. If all the variables that control the outcome are properly understood, then in principle, the mechanics that we understand can easily tell us whether it is head up or tail up. But the number of the parameters that control the tossing of the coin are so large that one cannot predict the future. Similarly, the weather forecasting was impossible, say, 50 years back, because the total number of the parameters that control the weather forecasting are very large, and the mechanics involved becomes complicated. But these days, since we have supercomputers and we can control a lot of data at a single instant of time, and we are able to almost predict accurately the weather. This is because the Newtonian mechanics is deterministic. So determinism lies at the heart of Newtonian physics. So any phenomena at classical level can exactly be predicted if the initial conditions and the nature of the forces is known to us. So this was the takeaway from Newtonian physics, that one can completely determine future if the initial conditions are exactly known to us. But at around 1900, our faith on these concepts started shaking, because we discovered new phenomena which needed a total rewiring of our mind, and completely different philosophy was required to have understanding of the phenomena that were coming up. So it all started actually with this man. We call him the father of quantum mechanics, because it all started by his his attempt to understand the black body radiation. So Max Planck, he was having trouble with what is called as black body theory. So we will try to understand, first of all, we'll try to understand what do we mean by black body, what was the problem, and how Max Planck was able to address this problem. So exactly in 1900, the problem came up. So let me give what the problem was. See, whenever a light is allowed to fall on an object, a part of the light gets absorbed, and a part can get reflected back, and a part get transmitted. This is how most of the materials behave. But one of the fundamental questions in physics was that, is there a body, if the light is allowed to fall on it, it completely absorbs it? So can we in fact construct at least conceptually such a body? And that body, when you allow light to fall on that body and it completely absorbs the radiations that are falling on it, that theoretically is called a black body. So conceptually, you can think of a cavity. Suppose we have a cavity and the radiation is entering from a hole. Then this within the cavity, the radiation is reflected from all the sides until it completely is absorbed. So any body, if where light is entering and then it is completely getting absorbed, that body is called as black body. But in physics, there's a principle that if a body is at higher temperature than its surroundings, then the body will radiate energy. That is the fundamental principle of thermodynamics. Now, if I assume this black body and I keep it at a high temperature, then instead of absorbing radiation, it will give out radiations. It will give radiations out from this pinhole. Now, these radiations which will be emitted by this body, they are called as technically called as black body radiation. So what is a black body radiation? It is the radiation emitted by a perfectly black body. So when these radiations which are emitted by a black body, when we analyze them, when we take their spectrum and figure out for what wavelength, what is the intensity, means for each wavelength, what is the corresponding intensity, then a graph was obtained experimentally. So how was this graph obtained? You can take any body, say you take a piece of iron and you heat it and then it starts emitting radiation. Then the radiation that the piece of iron will emit, that radiation is to be analyzed by spectrometry. We'll take the spectrum of that radiation. Then for each wavelength, there will be intensity corresponding to that radiation, and that intensity versus wavelength can be plotted. And it was seen that every object which is hot and is very close to black body, then it gives wavelengths which have different intensity it gives different wavelengths corresponding to different intensities, and there is one wavelength at which the intensity obtained is maximum, and that wavelength at which the intensity is maximum, that wavelength varies with the temperature of the body. What it means is that temperature of the body controls its color. For example, if the temperature is very low, then what will happen? The radiation at which the intensity at which the maximum radiation will be emitted will be in infrared region. So such things will not be optically visible. They will not be visible to the human eyes, but infrared cameras can actually locate such objects. For example, humans normally are at a temperature of around 32 degrees centigrade. At that very temperature, all we emit is very long wavelength infrared light. If we assume that we are also black bodies, and if we are moving in dark, we are actually black bodies that are at higher temperature than surroundings, so emitting black body radiation. Then ultraviolet, then an infrared camera will easily catch us because of the radiation that we are emitting. So infrared cameras actually work on this principle. So, but if the body is very hot, then it can emit even in the optical region. For example, body at a temperature of around 5,000 Kelvin can emit most of the energy in the visible region. And since we understand that the surface temperature of the sun is 6,000 Kelvin, so the most of the radiations that the sun emits lie in the visible region. So this was an experimental finding, and some empirical laws were derived from this graph, like the Stephan's law and the Venus displacement law. Stephan's law said that as you increase the temperature, you can see the area of these curves is increasing. So more the area of the curve, more is the energy emitted by a black body. And there was another empirical rule, which was that the shorter the wavelength, that as the temperature increases, the wavelength becomes shorter and shorter, or shorter the wavelength, more is the temperature of the body. And so the temperature of the body could be easily related to the wavelength at which it emits the maximum radiation. But there was the problem in physics was that there was no classical theory that could explain this graph. These curves cannot be explained by the known classical theories. At that time, the thermodynamics that we knew could not explain this curve. And this remained a puzzle in physics. It's called the black body radiation puzzle. So the classical theories that we knew, they predicted this kind of, the black line kind of graph. So it could see that the most of the, say at 5,000 Kelvin, this graph would be like, it is emitting more and more energy as the wavelength is becoming shorter and shorter. And at a very short wavelength, very, very huge energy is emitted. And this is a problem is called ultraviolet catastrophe, that everybody starts emitting madly in the ultraviolet region, which is not right, because we know that objects don't, any hot object doesn't emit most of the radiations in the ultraviolet region. depending on the temperature is what it would what kind of radiation would be maximum that it would be emitting. So the experiment was not experiment and theory were not compromising with each other. According to classical theory, this is what we get. This black line is what we get. But according to the quantum mechanics, according to the experimental finding, these curves were found, these blue, red, and other color curve. So these curves tell us that different temperatures would correspond to different kinds of curves, and the area of the curve would increase as the temperature goes up. In fact, the area of curve would be proportional to the fourth power of the temperature. So this was a puzzle. This was a puzzle that the known laws of classical theory are not able to explain the black body spectrum. These graphs which are obtained when a body is heated and the radiations from that body are analyzed. But so that was one of the puzzles we had in physics. So Max Planck came up and he thought that if you change the idea a little bit about the radiation, then this graph can easily be explained. So he proposed an idea that the energy of the radiation emitted by the black body is in packets. So this basically this black body, the energy that this black body emits, it does not emit energy in electromagnetic spectrum as a continuous form, but it emits energy in the form of small packets of energy, and these packets of energy now we call as photons. And each photon has an energy given by a relation E is equal to h nu, where nu is the frequency of that particular radiation, and the frequency can be written in terms of c by lambda. So he was able to propose that light is granular in nature. So the light is composed of small quantas of energy, and and if some thermodynamics can be done around that, then he was able to derive a formula now famously called as Planck's formula for the intensity of the radiation emitted by a black body, and that formula exactly matched with the curve that was obtained experimentally. So the only way to understand this curve that we obtained experimentally was to believe on the hypothesis that energy energy emitted by a black body is in quantas. It is not continuous, it is discrete, and energy of the light it can be expressed in terms of its frequency through the radiation is equal to h nu. This was a proposal that could actually help us to understand the black body curve. So this was a very big giant leap in our development of new physics. In fact, our concept that light is a continuous form of energy was completely discarded by Planck, and he had this new idea that light is not having a continuous form of energy. Actually, it comes in the bundles of energy, and these bundles of energy now are called as photons. So the interesting thing about this theory was that it was so simple and it could easily explain the experimental curve, which was obtained whenever you have a hot object that emits radiation, that more or less that object behaves like a black body. The radiations from all hot objects always have this black body radiation curve. And now we could easily understand, with the help of this physics, we could easily understand the color of stars. For example, the star that is at a lower temperature, it normally looks red because of the curve of the black body radiation is such that at temperatures which are around, say, 2500 Kelvin, the dominant radiation, the maximum, the wavelength at which the maximum radiation is emitted, or the maximum intensity is emitted, is red light. So if you happen to see some red star, then it's very clear that it's a cool star, cooler than the other stars. So then the star, like our own sun, is almost yellowish in color. The reason is that its temperature corresponds to the yellow color. So the Blackbody curve explains us that why sun is having the color that it has, because at 5,800 Kelvin, the radiations that are maximally emitted by sun have this wavelength of around 5,000. We have this wavelength around 6,000 to 7,000 angstroms. And then the blue stars are really very hot stars. So the stars which are blue in color have the surfaces are at a very huge temperature of the order of 18,000 Kelvin. So the Blackbody radiation curve allows us to map the temperature of different objects that we happen to see in the night sky. So that all is possible because we are able to relate the frequency or the wavelength with the temperature of the star through the Blackbody radiation curve. So this was a giant leap in our understanding, as I already said. So we had this proposal that light is composed of photons. So light, now we know, is at a fundamental level behaves like particles, because these are the packets of energy that flow in space-time, and we call these packets of energy as photons. So now there are other experiments that verify that light is also particle-like. Initially, remember that in classical physics we had this idea that light is wave-like because it was electromagnetic theory that controls the behavior of the light. Now, after Blackbody radiation, it turns out that light is granular in nature, at least energy is quantized. Now, are there any other experiments that back up this theory? Now we come up with a very, very interesting experiment. It's called Compton Scattering. And in this experiment, it is again, the understanding of this experiment is based on our concept that light behaves like particles, not like waves. So in this experiment, what we actually do, we take a photon, a particle of light, which we now call as the bundle of energy. We take a photon, which we call as incident photon, and we see its interaction with an electron at rest. Suppose we take an electron which is at rest and allow photon to strike the electron. Then what will happen? The electron recoils in one direction, and the photon will go in the scattered photon will move in the other direction. Now, this phenomena tells us that light is particle because the collision that occurs here is almost a collision between two material particles. We understand the collision theory. If there is a particle and then there is another particle, and this particle comes, moves, and strikes a particle at rest, then we know that they exchange momentum and they exchange energy. So the same thing happens here. The momentum and energy is exchanged between the incident photon and the electron at rest. The incident photon carrying some momentum gives energy to the electron at rest. The electron scatters in one direction, and the photon scatters with a lower energy and the greater wavelength in the other direction. In fact, one can calculate the wavelength shifted for photon using the laws of what we call as conservation of momentum and energy, means using the theory of elastic collisions. So one can figure out the shift in the wavelength is h by m naught c 1 minus cos of theta by just applying the law of conservation of momentum and energy. Now you can see that there's delta lambda has the dimensions of the length. This h by m naught c is also a kind of length, and this is called the Compton length. And this is very important when you go for advanced studies in physics. This plays a very interesting and fundamental role in our understanding. So this experiment was done, and the theory that backed up this experiment, called Compton Scattering experiment, is based on the phenomena that photons are not wave-like, they are particle-like. And so there is another confirmation that electromagnetic waves behave like particles. So very weird kind of thing, but that's how the physics shapes itself. So then there was another experiment, and this time it again confirmed the particle nature of light. So if it was seen that if one takes conductors, alkali metals, which are good conductors, then you allow light to fall on these conductors, then boom boom, they strike these particles, the electrons, and knock them out of the material. And this phenomena of emission of electrons from a metal surface, when you allow light to fall on them, is called photoelectric effect. And the problem was that the wave theory could not support this phenomena. So the experiment could be done in a controlled manner. What we do is we take a vacuum tube chamber, which is evacuated, and there is a positive plate, and that photosensitive plate is kept, there's a photosensitive plate and a positive anode, and the light is allowed to fall on the photosensitive plate. Electrons absorb energy from the light and they get emitted. And these electrons move from cathode to anode, and the current that is established is called anode current, and this can be controlled by controlling the voltage between cathode and anode. And there were many interesting results which were obtained from this experiment, and all those results were against the electromagnetic wave theory. If we take electromagnetic wave theory into account, then we cannot explain the results that we obtained in this experiment. And Einstein came up with a proposal that this theory can, this experiment can be easily understood if, instead of considering light as a wave phenomena, we assume that the light will propagate in the form, light is propagating in the form of particles called photons, and each photon has energy h nu. A part of the energy, the photon, the energy that the photon gives to the electron, a part of it is used by an electron in freeing itself from the metal surface, and a part of the energy goes to the electron as kinetic energy. So that equation, called the photoelectric equation by Einstein, explains this phenomena very well. In fact, you might have already some understanding of this experiment at high school level. That is a very famous experiment called Photoelectric Effect. So the moral of the story is that in photoelectric experiment, the light behaves like particles. If we assume light to be behaving like particles, then only and only we can understand its behavior. It's the experimental results that we obtain in the experiment on photoelectric effect. So it was seen that if the light was a wave, then these electrons will take time in freeing themselves from the metals. But what happens in the experiment, it is seen that when the light falls on the metal, at that very moment, without any time lag, the electron come out. And that, that's against the wave theory, because wave theory demands that some time will be taken by electrons to absorb the energy, because in case of a wave, the energy is spread all around. So it will, the part of the wave front will be attached to, will strike to an electron. Electron will take some time in actually adjusting its energy, absorbing energy, and then it will knock it out. And another thing was that if you control the number of photons, the intensity. So in wave theory, the intensity corresponds to the energy of the radiation. So if I increase the intensity of the wave, then I expect the energy of the electrons should go up. But in experiment, it was seen the opposite way. As you increase the intensity, it was controlling only the number of electrons, not the energy of the electrons. It was the frequency that was controlling the energy of electrons. So the wave theory was completely against the experimental findings. Therefore, a new proposal was needed, and that was proposed by Einstein. Einstein said that if you believe that electrons, these light is moving in the form of particles called photons, and each photon has energy h nu, and when they strike electrons, they strike it like particles colliding with electrons and giving entire energy to the electrons. The electrons use that energy, utilize that energy, part of which is used by liberating from the surface, and a part goes as kinetic energy with the electrons. So that also experiment, now we had experiments coming which completely tell us that experiments are telling us that these